parameterization for SLE. Thanks.
Thank you, Laurie. Okay, so I want to say happy birthday to Greg as well. I got to thinking about it last night, and I first met Greg at the Random Shapes workshop in 2011 in IPAM in Los Angeles. And my first thought about that was, I hope no funding agency starts looking at things and wondering why in 8 years we've only gone from random shapes to random geometry. But I think we'll be okay. So when I went there, I was very much hoping to meet Greg. I already knew he was a very important and influential mathematician with several, very nice papers that I was familiar with and that I appreciated for their clarity. And then when I got there, I was very happy to see that, to find out that he was a very friendly and personable person who was very generous with his time and helping graduate students. And he's helped me a lot in the last however many years, I don't want to say. But I really appreciate that, so thank you. Okay, now at the same time, I also realized I could say that about many people, and many people, many such people are in this room. So I wanted to say something that also kind of distinguishes Greg to me, makes him stand out and is unique in my mind. And that's a story about, that happened about 5 years ago at the PIM Summer School in Seattle. So I have to thank Chris Birdsey and Stefan Rhoda for organizing that as well. But the story is, it means that basically Greg is, I think, the only person I know in this room, and only one of 3 math professors who I've ever seen perform live karaoke in front of a bar that was half full of strangers. And if you weren't there, if you missed it, let me tell you, you really did miss something. That was quite an event, actually. If you want to know what Greg is like in karaoke, if he's different from his lectures, well, I mean, he was full of confidence. He just, he went for it. There was no hesitating whatsoever. He might have had 1 or 2 beers in him, but that's par for the course at karaoke. The song he sang was the Rolling Stones' "Paint It Black," which I think we can all agree is a very bold choice. That is not an easy song to do at karaoke in the best of times. Now, I'm not going to say anything about Greg's singing voice, but I will say that he did know all the lyrics. He didn't have to look at the screen at all. He had it all down pat. Do you remember this?
Vaguely.
So there might have been some liquid courage then, hey? Actually, I remember it. I was a bit annoyed with myself because I'm pretty sure I took a picture that I would be able to share, at exactly a moment like this sometime in the future. And then I'll be damned if I can find it. I don't know where it is. So then I just, to combat that, I did some Googling, and I found an image online that kind of captures the what that night was like. John, it looked kind of like that. And I mean, okay, so there might have been some of this. There might have been some of that at one point during the song, but by the end, hands down, Greg was the hero of the bar. He had a standing ovation. He had a crowd of very excited graduate students up. They're all chanting his name, and pretty soon the rest of the bar, full of locals, they all join in as well. So the karaoke guy was pretty impressed. All right, that's my story of Greg. Okay, so now I should probably talk about some maths. And I decided that for this conference, I'm going to talk about natural time parameterization. So this is something which hasn't really been discussed a lot, except maybe a little bit in Frederick's talk. And in the last 10 years, it's been a very active field within SLE. And by and large, I think it's fair to say that most of that is due to Greg. I mean, there's many of his co-authors and students involved, but all the major papers have Greg's name on them. So what I'm going to tell you about is natural time parameterization for SLE curves with kappa less than 8. The boundary measures part of the title is that's sort of an analog of what happens when you look at the SLE process on the boundary for kappa between 4 and 8. And I have a few works in there. That's why I figured I was qualified a little bit to talk about this. And so most of what I'm going to say is just summary and a review of things that Greg has done and some very recently. But at the end, if I have time, I'll tell you about some future work/ideas that for the boundary measure that I've been discussing with Frederick Wickland. Okay, so Let me just quickly review, how SLE is parameterized normally, which is by half-plane capacity. And now, first of all, since this is Greg's conference, I have to parameterize SLE in the Loevner equation in the way Greg does, which is he uses this parameter A instead of a 2 up there, which stands for 2 over kappa. And the driving function ut is actually the negative of Brownian motion. Okay? And under this definition, I'm sure everyone knows, the half-plane capacity of the curve at the time t is just A times t. Of course, half-plane capacity for a set is given by this type of formula here. Tau A is the time at which your Brownian motion either first hits A or exits on the real line. So, of course, this is a very natural time parameterization for complex analysis, but it's not so natural for probability. In probability, well, of course, SLE is the scaling limit of discrete curves, and all the discrete curves we study come with natural time parameterizations. The usual one is just 1 unit of time per edge that you traverse, especially if you're working on some sort of regular lattice. So just a quick example of that would be to say take a loop-erased random walk, something like this, in an n by n square on the square lattice, which you can't see, and you parameterize this thing so that it has 1 unit of time per edge that it goes along. Okay. Now, to get the natural time parameterization, well, you want to take a scaling limit of this thing as n goes to infinity. So make the mesh size 1 over n, but then, of course, speed up the way, how fast the curve goes along the trajectory. Well, in this case, you do it according to this n to the 5/4 scaling factor, building off this long-standing conjecture that the number of steps is like n to the 5/4 for loop-erased random walk. If you use a different model here, of course, you'll put a different exponent. With Brownian motion, of course, it's typically n squared for simple random walk converging to Brownian motion. And of course, since this is convergence in law, you need some sort of topology, of course. And it's typically, it's just typical soup norm difference. But you should also have some term that accounts for the fact that different curves can have, they last for different times. Right? I'm not sure if this is actually what Greg and Frederick are planning on using, but of course, it's your choice. So now, as we heard in Frederick's talk, the full convergence of loop-erased random walk to SLE2, well, this is still not proved. There's these nice papers he was talking about that are steps in progress, and it sounds like they're more or less there. In that vein, I'm just going to briefly mention a small paper that myself and Mike Kosdron and Rob Masson, a former student of Greg's, put out a few years ago. And what it was an attempt to try and understand the steps that would need to go into showing that a discrete time parameterized curve converges to SLE in the natural time parameterization. And so we tried to give a framework that was sort of just an extension of what has already been done in the Lawler, Schramm, Werner papers, and is in some sense, it's clear exactly what more you need above what has already been done. And I think we did an okay job of outlining it in that paper. And then we got to the key step in that, which is showing that the discrete Green's function converges to the continuum Green's function, and we basically went, and we realized we had no hope with that. We came up with some estimates that for these things like the probability that a loop-erased walk goes through an edge, but we couldn't get rid of the nasty logarithmic factors that kind of plague everyone since the time of Rick Kenyon's papers. It took Greg to come along and do that in this paper here. So that's just a little plug for that paper. Now, okay, so if you're trying to study natural time parameterization by doing scaling limits of discrete things, that's a hard problem. I mean, that's just hard. I think it's always going to be hard, no matter what curves you're working with. But it was realized early on that despite that, it's still possible to define and analyze what should be the scaling limit directly for the continuum curves. So if you work exclusively in the continuum, you can talk about natural time. You can understand natural time. So that's what I'm going to talk about here for the next few slides. I'm going to do it in a way which is a little bit different from how Greg usually does it. This is just my preference. But I like to describe natural time parameterization via the occupation measure instead. And so occupation measure for a curve is just a simple thing. For some set A, the occupation measure is just the amount of time the curve spends in A. Simple thing. And of course, this thing will be supported on the trace of the curve. Its total mass will be, however long the curve is time parameterized for. And finding the natural time parameterization for the SLE curve is just equivalent to finding the natural occupation measure. Right? I mean, of course, if you have the curve in natural time parameterization, then you immediately get the natural occupation measure. If you have the natural occupation measure, and you have at least the curve in one particular time parameterization, say like capacity time, then it's very easy to convert to natural time. You just set this gamma star will be the curve in natural time. It's just this gamma in this particular time run on this time scale, sigma t, where this sigma t is chosen such that, well, the measure at time t is t. And that's the complete analog of what happens in the discrete case, right? 1 unit of time per edge is the same as saying that at time n you have n units of length. So that's how I talk about it in terms of occupation measure. So why would it be hard to come up with an occupation measure for the SLE curve? Well, I mean, the simple answer is that, the curve is a fractal set. And putting measures on fractals is not always so easy. Of course, there's Vincent's nice result that the dimension of the curves is 1 plus kappa over 8. Now, given such a fractal set, if you want to put a measure on it, I mean, there's many ways you can do it. I think maybe the nicest thing to do is go to Kenneth Falconer's book and open it up and find one of these nice constructions like Hausdorff measure or Minkowski content, and show that with probability 1, one of them gives you something that's meaningful for SLE, right? I think well, I'm going to talk about that on its merits. I think that's the best way to do it, but not always possible. In fact, the first way it was done to construct this natural time occupation measure was probabilistically using the Doob-Meyer decomposition. And that's what I'm going to talk about first, and then I'll go and talk about the recent work on the geometric construction of it. Just before going on, though, let me say, once you've put a measure on the curve, how do you know that you have the right one? I mean, you can put many measures on the curve, obviously, right? What should tell you that you have the right one? And I'll say this in a bit, but there's some nice properties the measure should have. It should have a domain Markov property, a conformal covariance property, and then certain measurability properties, which are not so crazy. Let me just briefly say that, when I think of this, I always think about the analog between these two ways of constructing the measure, geometrically and probabilistically. A good analog to keep in mind is just the local time on the zeros of a 1D Brownian motion. Okay? If you remember, that set has Hausdorff dimension 1/2. A classical way to build a measure on that set is just by, the Doob-Meyer decomposition of the sub-Martingale absolute value of Bt, right? You know that this thing has such a decomposition. Since this process behaves like a martingale when it's away from 0, you know that the increasing part is only increasing when you're actually at 0, and so this LT process is actually a measure on the zeros, right? And then of course in some measure, and then by this sort of bastardized version of Tanaka's formula, it's kind of the measure you want. That's the probabilistic construction of the measure. The geometric construction, it exists. I don't think it's as well known, but it very well exists. It's given in this paper by Sam Taylor and Wendell back in 50 years ago. And what they show is that the local time measure agrees with the Hausdorff measure on this set, where the gauge function for this thing is given by this root t with some log factors. Okay? So you notice, of course, the dimension is 1/2, but to get a meaningful Hausdorff measure, you need these log correction terms. Kind of a standard thing with these random fractals. So let me quickly go through here and say a few words about these properties that you hope that the occupation measure should have, and why you expect them to be this way. The first thing is I'm going to talk about this measurability property. So this occupation measure, nu gamma, well, it should be measurable with respect to basically the trace of the curve. The idea is that, of course, you want this to be a measure coming from some geometric construction. So as long as you just see the curve, its geometry, that should be enough to build the measure. Okay? So that's the first assumption. And one way to say that is that it's measurable with respect to gamma tilde, this equivalence class of the curve, modulo reparameterization. And just a small extension of that is saying that, at every time t, if you look at the measure restricted to the curve up to time t, then it's determined by the equivalence class of the curve up to time t. So that's the measurability assumption you'd like to have. The next one is the conformal covariance property of the curve. So basically, how does it behave under conformal maps, right? Under transformations by conformal maps. So of course, we know that the curves are invariant under maps, but the measure should not be. And the simplest way to see that is just take the curve and blow it up by a factor of r, right? Blow up everything by a factor of r, and the measure should scale by a factor of r to the d, since this is a d-dimensional set where d is this number 1 plus kappa over 8 that's Vincent's, right? And so that's how it should behave under scaling, and of course under general conformal maps, well, it should behave locally scaled by a factor of the modulus of the derivative, right? That's the complete analog. And then once you have a rule for how this measure should scale, transform between different domains, then you also have the domain Markov property for it. Okay? So if this red part of your SLE curve is the part you've already observed, the blue is the future unobserved part, then of course when you apply this map, well, ht, which gets rid of the red part and centers everything back at 0, then this is a new and independent SLE. Right? And the statement of the domain Markov property for the measure is the exact analog. When you transform this thing covariantly by this d-dimensional transform, then the measure you get, when you transform that measure over there, it's a new and independent SLE measure corresponding to this blue curve over here. Okay? And of course, the important thing is it's the thing you get over here is entirely independent of the red part over here. So that's the conformal covariance property, the domain Markov property you would like for your curve, for your measure. So let me just quickly give the definition of how you use this, given these properties, how you use this Doob-Meyer decomposition to define the actual occupation measure. Okay? I'm just going to state the definition, then I'll explain it. So first take a chordal SLE curve, say in H in the capacity parameterization, and then you look at the process. How does the measure change as the curve grows? And what it's defined to be is the increasing part in this Doob-Meyer decomposition right here. Okay, so I have some fixed subdomain D. What I do is I take a specific martingale, which I'll talk about in a second. I integrate it over the domain. This quantity turns out to be a super martingale in T. And so by Doob-Meyer, it has a decomposition as a martingale minus an increasing part. So I always call it increasing part, even though it's it's minus an increasing part. So this MTZ, this is a martingale given in terms of the conformal map between the domains and the SLE Green's function, which is this quantity here. Okay. For right now, all we have to know about the Green's function is exactly what Frederick said. The Green's function describes the probability that the curve goes through a small ball centered around Z. Right? And there's these little wavy things that tell you how that depends on epsilon, how that decays with epsilon, and I'll say more about that later. So this is the definition of the occupation measure as a process in T. Now, why is this the right definition? Well, I'm going to try and explain this in two ways. I'm actually going to use the second way first. It's the right thing in terms of the SLE Green's function. And then I'll come back and explain why it's the right thing using domain Markov property and conformal covariance properties. Okay? Basically, if you assume conformal covariance plus domain Markov plus the measurability things, this is the only form you can have for the occupation measure. But let me explain it first in terms of the SLE Green's function. And I'd like to explain it using these pictures. And in fact, being able to show these pictures is half the reason I wanted to give this talk again. So this is just the idea of the Doob-Meyer decomposition for building this measure. You can already see it on the discrete level. Okay, you don't need to go to the continuum to understand the motivation. And what you start with, so here's this random curve I had before in some n by n square. Say it's a chordal loop-raced walk from this point to this point. And for the occupation measure you want to put on this is just arc length, right? Perfectly well defined here. So put arc length on that curve. Okay, now in this picture, I'm going to cheat. Instead of putting arc length, what I'm going to do is I'm going to put unit mass 1, or possibly some constant mass, let's say, at all the vertices that the thing goes through. I mean, same thing, doesn't make a difference, right? Just for the purposes of illustration. And the idea of the Doob-Maillard decomposition is that to get this picture, this measure, what you do is you actually start with this. Yeah. Now, with these colors, this is not an eye test, by the way. What these colors are is, what they represent at least, is these are the probabilities that your random curve will go through each vertex. Okay? Just given by the colors between 0 and 1 there. Just a word of warning, this is just conceptual. This is not actually anything real. This is art. So what you do is you start with this picture, all the probabilities for going through the different sites, and then you start exploring your curve. Okay? So you make one step up, and then now you recompute what's the conditional probability of going through all these different sites, given what you've observed so far. And so the colors all change, right? And you keep doing this over and over as your curve evolves, and blah, 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 blah. The colors change, and the ones along the curve, of course, just go to 1 and stay there, right? So, I should have automated this. So you just compute these probabilities as you go along. Now, this movie, as it evolves, of course, that by definition is a martingale, right? It's just conditional probabilities as the thing evolves. So you're watching a martingale in action. This martingale now, what it ends with is this. This is the final time value. But this martingale, you can easily write down its Doob-Maillard decomposition. Okay? It's very simple. You want to write it, you want to decompose it into a super martingale. Super martingale minus an increasing part. No, super martingale plus an increasing part. Yeah, that's right. You want to write this as a super martingale plus an increasing part, and the way you do it is you split it up into 2 parts. This is the initial super martingale, the initial value, and you just move all the red parts over here. Right? So now this picture here is increasing. This guy has to be a super martingale because their sum is a martingale. Right? And so this is the unique Doob-Maillard decomposition of, of that first picture. Okay? And what it ends with, the final time value of the increasing part is exactly the measure you want. Right? Okay. So this tells you, what you should do in the continuum instead. And the idea is, in the continuum, building this part is horrible. It's on this fractal set, so what do? But this side over here, this evolving movie, you can do that pretty well, because everything there is happening off the curve. And like in one of Greg's books, he writes somewhere, the way you study SLE is by studying what happens off the curve, not on the curve. This is just another example of that phenomenon. And so what you need to understand in the continuum is just, the conditional probability of a curve going through any given point. Right? And that, of course, is given just by this SLE Green's function. So there it is again. The formula for the Green's function, its relation is the probability of going through a ball. This, of course, was first discovered in a paper by Stefan and Oded. I'll just briefly plug, there's this paper by myself and Mike and Greg. We analyzed the Green's function for the radial SLE case. We don't have an explicit formula like this nice one up here. It's tough to get one because there's no scaling property anymore. But we have a characterization of it in terms of the expected value of certain processes at certain stopping times. And as Namgyu Kong mentioned this morning, there is actually that formula simplifies and becomes something very nice and explicit when kappa equals 4. I'll just say, of course, now so many, since this first result by Oded and Stefan, there's been many results or many refinements of how sharp this thing is. And excuse me, I think the first asymptotic statement of this type came in Greg's Park City lecture notes from 2007. I actually remember that. I remember it was a big thing when Greg figured that out. So how to get these asymptotics. It was for me, at least. And what the result is, it's not for the distance to, it's not saying that the distance to the curve is less than epsilon. It's measured in terms of conformal radius, which is, somehow a more convenient way of measuring distances in this world. And this one thing I should mention is the C star you get here, it's explicitly computable in this particular construction. Now, of course, so by conformal covariance, of course, you know what the conditional probability of going through a ball is given this formula. It's just, the standard picture. You conformally map back, and this ball becomes centered at this point here with radius this times gt prime modulus, right? So that's how you get this formula for this is the continuum analog of the moving color picture, right? The moving color field. And that's what tells you that you should integrate that in the continuum to get the occupation measure for SLE. Another characterization of this Green's function, if you don't want to describe it as being the limiting form from this formula, you can also just say it like this. It's actually the unique function such that it has a scaling relation in terms of this d here is the dimension of the curves again, and this quantity here is a local martingale. Yeah. Those two things uniquely specify the Green's function. And in fact, that's the whole idea behind why conformal covariance plus domain Markov property uniquely determines the measure, the occupation measure. If you have, say, the measure of a set A, and you take the expected value of that given the curve up to time t, well, that's going to be a martingale since it's conditional expectation. But you can decompose that thing into the parts that you've seen plus the parts that you haven't seen. And the parts that you've seen are measurable by this measurability assumption. The parts that you haven't seen, you can exactly compute their conditional expectation based on the conformal covariance plus domain Markov properties. In fact, those two things uniquely tell you that this thing has to be exactly what you're integrating to get the occupation measure. And then, of course, to get the actual measure, you just take t goes to infinity for this thing, and since this measure will be supported on the curve, you'll be done. Now, a nice little benefit of this construction, again, you're just taking this as your super martingale, saying do Maillard decomposition, increasing part is my measure. A nice benefit of that is since this thing is uniquely specified, and the output of the do Maillard decomposition is unique, that says that the measure is also unique. It follows straight away. So this is the unique measure-valued thing that has these properties, measurability, conformal covariance, and domain Markov, up to some multiplicative constant, which, of course, we never care about. So, okay, what's the difficulty in all this, right? The recipe seems to be just do Maillard and you're done. Well, it would be nice, but unfortunately, that doesn't work. It turns out there's not always a non-trivial decomposition for these do Maillard type things. And to understand that, you end up entering this weird, or maybe not weird, but sometimes unfriendly world of local martingales. So let me just say a few things here. So, first of all, a positive local martingale, that's always a super martingale. That's just Fatou's lemma, I think. So for example, this process here, this mt of z, which is the color changing picture, that's a super martingale for every z. Okay? And in particular, when you integrate it over a domain D, it's still a super martingale. That's just Fubini's theorem. But it turns out that for each fixed z, this is kind of it's a super martingale, it's also a local martingale, it's not a honest martingale, in the sense that its expectation is not constant over time. I mean, you can compute the expected value with respect to t, and it decays. So this is something that's called a strict local martingale. And one of the things that happens with this is if you look at the do Maillard decomposition of this thing, of this super martingale, it turns out to be pretty boring. So one thing you can show is that, up until a stopping time at which the SLE curve gets within distance epsilon of z, this is actually an honest martingale. It's bounded basically, so the bounded thing is going to be a martingale. The problem is if and when the curve actually goes to z. I mean, of course, with probability 1, it doesn't for a fixed point. But so that means that the do Maillard decomposition of this thing, since it's a martingale up until the curve gets to it, the do Maillard decomposition, the increasing part will just be identically 0 the whole time. Okay? So it's completely trivial. Even in sort of the exceptional case when z is on the curve, the do Maillard decomposition of that thing is just flat until the curve actually gets to z, and all of a sudden it jumps up to infinity, and then it dies off. Right? That's how I think of my dating life quite often. It's like nothing, 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 then all of a sudden way too much, and then it dies off. So to show these things, like you have, that you actually get a non-trivial Doob-Meyer decomposition, you have to show what's called this class D property. Okay? And this is a bit of a fine thing. It's actually not, so what you need is that, if you look at your martingale, your super martingale M, but evaluated at general stopping times, almost surely finite stopping times, you have to show that this is a uniformly integrable family. Okay? It's not enough to just do this at finite times, or deterministic times. I think in one of Rick Durrett's probability books, he wrote something like that it was enough. And then I think he got several comments that no, it wasn't quite right. And so, in later volumes, there was a very nice correction of that. So, what is the actual hard part in this Doob-Meyer construction of the occupation measure? Well, it's in showing that this super martingale here has this class D property. Okay, that's where all the work comes in. And at the start, why should it be? Because every single one of these things for each fixed z is not a super martingale. Or, sorry, it doesn't have the class D property. It is a super martingale. It doesn't have the class D property. So why should it be that it does when you integrate them? And, okay, it does. It's basically because, within the set D, if the curve goes through there, there is some exceptional points where, these things blow up to infinity. And, well, that's enough to give you the class D in this case. I remember explaining that to Mark Yor, though, many years ago, and he thought it was very peculiar. So what you need to do now to apply this class D stuff is you have to show that this type of quantity here is uniformly bounded in T, right? Some sort of uniform integrability. Of course, you only need 1 plus epsilon moment for this type of uniform integrability, but since it's an integral, well, you square. What else are you going to do to compute a moment of an integral? So all that work of trying to verify, this class D property for this particular submartingale, well, it's split up into many different papers, but it started off in this joint paper between Gregg and Scott Sheffield, where they started. This is the first place where this natural time parameterization on the curve appeared, and there's many technical estimates in that paper, and what they use them to show is that basically, you have these sort of uniform L2 bounds for a range of kappa which doesn't go all the way up to 8. It goes up to some funny number, 5.071, ... This number is meaningless. It just turns out to be, it's an artifact of the proof. But in going through their paper again, and in light of Vendelin's talk on Monday, something, well, coincidental popped up, is that this constraint here, it turns out is actually because of there's an equation like this sort of duality sum has to be bigger than this mysterious 3.5. So,
Yeah. I got my wrong for 3.5.
Oh. I waited all week for this. Can you go change the paper, Greg? So it's 3.6
we got it wrong
now.
too.
Yeah. So okay, maybe 3.5 is not going to be the hero of this conference. But so this restriction on kappa, though, it's entirely artificial. But all these nice ideas, though, are contained in this original paper. The technicalities were just elusive. Let me give just a quick sketch of how the proof in there goes. The first step is to change variables in this equation. And you change variables so that every quantity in Z is now written in terms of the inverse map of the SLE map GT. And then you use some equalities in law to replace that with things involving the reverse flow. So everything becomes now in terms of the reverse flow for SLE rather than the forward flow. I actually find that kind of interesting in terms of Frederick's talk, because he mentioned they're sort of doing the analog of this for the discrete curves. As it evolves, you have this sort of way of writing down the, I guess, corresponding super martingale in terms of the increasing process, in terms of the sort of reverse flow thing, or is it the increasing process? Or, I don't know. I didn't understand too if what you're doing in that case is more of it's a corollary of your result, or if it's the technique you're using to. It's the technique you're using. Okay. Okay. So you're using sort of a discrete version of this same idea. So you write down this quantity in terms of the reverse flow, and then you just go ahead and discretize time for this process. Not switch to a discrete model, just discretize the continuous time. Okay. And for this discrete time process, you just go ahead and write down the increasing part of the Doob-Maillard decomposition. Actually, it's only an approximate increasing part of the Doob-Maillard decomposition, but you can do it. It's all written down in terms of the reverse flow, and then you take a limit of this thing as the time step in your discretization goes to 0. And you need some sort of, you get limits almost surely, but you also need some moment type limits, L2 or something like this. And this type of idea of discretizing time and then taking a limit, that's how most proofs of the continuum Doob-Maillard thing go. I think in particular, Greg was very influenced by a paper of Rich Bass on this from late 90s or something. Yeah, in that type of computation. Just another quick plug mention. This same idea, Scott Sheffield and I used it in the boundary case when you're looking at, you have kappa between 4 and 8, and the curve makes these non-trivial intersections with the real line, and the dimension of the, this set is this number 2 minus 8 over kappa. We used this same sort of Doob-Maillard idea to construct, the same analogous measure on the boundary using the same idea, just integral of the, conformal Green's function type thing on the boundary, and everything goes through. The main difference, though, was that the technicalities turned out to be a lot easier in our case, and that's because we had this. We had the second moments estimates were handled by a two-point martingale that had just been worked out by Oded Schramm and Wang Zhao from Singapore. And we had a bound of the form, well, you have this martingale, which is the conformal Green's function. If you multiply two of them, then this decays like x minus y to the d minus 1 here, since we're working in a one-dimensional set. D is this number here, but whatever. The only important thing here is this actually doesn't depend on the stopping time, this bound. It's independent of whatever stopping time you plug in there. Finite stopping time. So, shortly after the Lawler-Sheffield paper, this restriction on kappa, this whatever, 5.0, was removed, and they were able to get the result, the full Doob-Maillard result for all kappa less than 8. And this was again with a paper with Zhao Wang from Singapore. And what they did is they did sort of things that they ended up getting results that in the end they are closer to what Scott and I did for the boundary case. The way they get them though had to be very different. In the boundary case we had this nice estimate, but it came from a very explicit two-point martingale that I imagine Oded found using some just cleverness, really. And but since it was one-dimensional, he was able to reduce things to solving an ODE, and that's how he got the two-point martingale, and then these bounds. When you're working in the bulk, well, those types of two-point martingales aren't readily available, so you have to do a lot more work to come up with these types of estimates. And the work to do this, well, so I think Greg can correct me here if I'm wrong, but I think this estimate first was based on what Vincent Bafara had in his dimension of the SLE curves. Greg and Zhao were able to get this estimate based on Vincent's estimates. But they very quickly replaced that because their final write-up uses another nice paper of Greg's, uses the two-point Green's function, which he wrote up in a paper with Brent Verness. This nice paper, multi-point Green's functions for SLE and an estimate of Bafara. And what they do in this paper is, they study this normalized probability of going through two distinct points, and they do a very fine analysis of this thing using, some techniques I'll talk about. What's called this radial two-sided SLE that Greg is very fond of, and some very sharp estimates on, controlling how often the curve goes back and forth between 2 points z and w. It can't do this without paying a huge penalty. And well, I'll say a few more things about that in a bit. But using this Green's function proof, they were able to get this bound here, which in turn gives them the Dube-Mayer thing. Let me just say a quick few things again about this paper with Brent. One thing they were able to show is that there is this 2-point Green's function such that you get this limiting probability for the conformal radius around points z and w. Okay, and the nice thing here is, oh, I wrote it wrong, but this should be, one of these should be delta, I guess. The nice thing here is you have a ball of independent radii around the 2 points z and w, and you can take them to 0 however you want, and you always get the same limit, which is this. This is the same C star that appeared in the earlier slides, and then this quantity G of ZW. And in contrast to the boundary case, an explicit form for this G of ZW is not known. If it was, I think a lot of people here could just retire, make our lives a lot easier. But they did give a characterization for it. They gave a formula for it. It's just 1 point Green's function at Z times 1 point Green function at W times this quantity here. It has a description in terms of what's called this two-sided radial SLE measure through Z, that should say. This is just you take the chordal SLE from 0 to infinity, and you condition it to pass through Z, basically, using the local martingale that I prescribed before. Just one thing I'll say is, since that's a local martingale, you have to do some care. There's some care you have to take with doing that type of Girsonov type tilting to get this two-sided radial SLE measure. How you should think of these two terms, though, is well, this product right here, that's just the probability of first going through Z and then W, and the second term is the probability of going through W and then Z. Okay, so you get this nice formula for it. Again, there's no explicit form of this thing, but I'll just mention oh yeah, first of all, before that, so this is again a statement about conformal distances to the curve. This again was improved by Greg in a paper from not too long ago, I think. A joint paper with his student Mohammad Rezai, who is now a postdoc at Michigan State with Dapeng Zhang, and unfortunately couldn't be at this meeting for reasons entirely beyond his control. So they were able to replace these with actual distances, not conformal distances. And then in an even more recent preprint, I think just a few months ago, they were able to give up to constants bounds on what this G of ZW formula is. So it's an explicit function, it's simple enough function, right? That gives you an up to constant bound on what the 2-point Green's function is. Right. Okay, so now I'm just going to end here with a few more comments about this Dube-Mayer decomposition before I move on to the geometric construction that Greg has been working very hard on in the last few years. Just a few more comments, though. So, what are some nice things about this Dube-Mayer construction? Well, one immediate thing is that you get this measurability with respect to the independent of the time parameterization of the curve that you're given. Right? A simple way to see that is if you're given a different time parameterization, that just time parameterizes. That gives a different time parameterization for the super martingale. But with the Dube-Mayer thing, if you time change the super martingale, it just time changes the parts as well. So you get invariance of the measure of this thing in that way. Another positive of this construction is that there's soft arguments that give you the existence of the conformal Minkowski content. Okay, so this is something that we worked this out in the paper with Scott, and then it later appeared. It also appears in the paper in Greg's paper with Zhao Wang. And what this is, it's sort of another way it's a probabilistic way of measuring distance to the curve. You look at all points. I guess I wrote this in the boundary case. You look at all points on an interval at which this this Green's function martingale gets to a certain height. It gets sufficiently big. Right? And then remember, what that tells you is that in some sense the curve is close. If that happened, then the curve is close. Using the Kobe 1/4 theorem, you can work out what close means exactly. So you just look at this set of points where the curve is close in this martingale sense. You scale it by this, take the Lebesgue measure, that's these bars as the Lebesgue measure, and then scale it by a factor of epsilon to the d minus 1, and try to take a limit of this as epsilon goes to 0. And in fact, we were able to show that limit exists, and the way you get it is, well, you can recognize that this quantity here is actually the increasing part of another Doob-Maillard decomposition, sort of an epsilon regularization of this MT process. And what you do is you just take this MT thing and you stop it if you ever get to height, whatever, this height here. Right? And then this integral, which is now since that's a martingale now, since of course everything is bounded there, you split that up into the parts that haven't yet reached this height plus the parts that have reached that height. And that's increasing. And you can show that this part will converge to this part, since the measure of the points where you don't reach that height goes to 0. And well, since that goes to that, there's a nice theorem in the Doob-Maillard theory, which comes from this book of de Lacherie and Maillard, that tells you that the parts also converge. And so you get a soft proof of convergence of this thing. Actually, it was actually, for this result, it was actually Yves Lejeune that pointed me in the direction of this. I doubt he remembers that. But, and the direction was, well, go talk to Mark Yor. And so I went and talked to Mark, and I knocked on his door, and, I explained the problem to him. And okay. And he gets up, and he goes down, this is in Jussou, and he goes down to the library, and he turns, and he goes right to the bookshelf, right to the exact shelf. He says, I think this was in the Séminaire des Probabilités, 1969. And he pulls the thing out, and opens the book, and sure enough, there it is exactly right there. And in talking with him, I don't think he was actually like didn't use this thing maybe ever. He just remembered this from forever ago. And then afterwards, he asked who I was. I'd forgotten to introduce myself. So. So that's one of the nice things about the Doob-Maillard thing. A shortcoming is that it's not clear if this thing actually corresponds to something produced by a geometric method, like Hausdorff measure or Minkowski content. For example, do you have invariance under reversibility? If you take one simple path, or a single path, a realization of a path, and instead of growing it from 0 to infinity, if you grow it from infinity to 0, do you get the same thing? I mean, if it's a geometric thing, of course you should. But in the Doob-Maillard thing, since you've changed the evolution, you might get something different. It's not so clear. Another case where you don't necessarily have invariance is under boundary perturbation. I mean, if this is a realization in the half plane, it could also be a realization in the half plane, h take away some blob. And if you, if the measure really is a geometric thing, it shouldn't care where it was sampled from, right? But the Doob-Maillard thing does care because these things have different probabilities. And so is it invariant? It's kind of like, if you go back to the example of the 1D Brownian motion, and if you just take the 1D Brownian path and you do some crazy stuff to it on the excursions away from 0, does the local time part stay the same? You didn't change the set, but the geometry, the Doob-Maillard thing it doesn't like that. So I'll just briefly mention in this case, invariance under this type of boundary perturbation, or what this was done in a paper by Greg and Mohammed again. They called it independence of domain, I think. And this is a paper, basic properties of the natural parameterization, that I don't think they actually ever published. Is that right?
Oh, you did a lot of research to find this.
Oh, yeah? Well, the internet, Greg, the internet. Yeah, so this
will never be published.
Yeah, it'll never be published. No, their next paper superseded the results in here, so one of those situations. One thing I'll mention is that they were able to show also that if you take your curve and parameterize it in capacity time, then this increasing part of the Doob-Maillard thing, it's Holder continuous with an exponent that they don't know, but it tells you that sort of, the difference between the capacity parameterization and the natural parameterization, it's definitely going to be a rough thing, but at least it's not too rough in a Holder sense. Okay, so what about geometric constructions now in the last few minutes? Well, so you want to just, given the set, show that some geometric construction applies with probability 1, right, and gives you something meaningful. I think, the thing everyone sort of likes the most, for some reason, is you take the Hausdorff measure, right? Find the Hausdorff measure on the curve such that it's equal to the part coming from Dublayer, just like with the Brownian zeros case. Well, okay, it's been folklore for a long time that if you put in, for your gauge function, if you just put in the power function, epsilon to the d corresponding to where d is the dimension, you should get 0. I mean, this is the typical thing in these sort of random fractals cases, and we saw that with the Brownian zeros. And actually, Mohammed finally proved this, wrote it down in a nice little paper from a few years ago. What's the typical reason here, of course, is if you want to, there probably is a gauge function for which this is true, some phi for which this actually, you get equality here. I don't know if anyone really has any good ideas for what this would be. In one of his papers, Greg writes quite nicely that what you need is an idea of you need some estimates on the upper tail of the amount of time that an SLE curve spends in a disk. Okay? And that type of thing is very hard to come by because, if SLE spends a lot of time in a disk, it really changes the distribution of the future SLE. In fact, a lot of Greg's work in this geometric stuff is showing that typically when the amount of time an SLE spends in a small disk does not change the distribution of the future thing. That's kind of the moral of how the rest of his work goes. So Hausdorff thing it's still elusive, but finally now we have some geometric constructions of this natural time measure, natural occupation measure, and it's in this paper by Greg and Mohammed. This is the one that supersedes their earlier paper. It gives you the Minkowski content of the SLE curves. And what they do, of course, is you take all the points in the upper half plane such that the distance to the curve is less than epsilon, take Lebesgue measure, scale this with this power scaling as epsilon goes to 0, and this limit exists. That's their main result. It exists, and it equals the thing you get from the Dublayer construction up to some, again, fixed multiplicative constant, which, whatever. A nice consequence of this construction is that right away you get this invariance under boundary perturbations and reversibility. This construction only cares about the geometry of the curve, right? The actual set of points. Doesn't care about any kind of the way it was growing, anything like that. And they show that in full generality too. One small little downfall about Minkowski content, this type of thing, is that it's not immediately known that it's an additive thing. Might not be a measure. It's not true in the epsilon level, so why would it be true in the limit? But in this case, they managed to show that it is true, and just an extension of what they show is that if you look at the double points of the SLE curve, when kappa is between 4 and 8, then the Minkowski content is actually 0. Right? So it's not unexpected, but it's good to know. And a key step in their proof of all these things is a refinement of, this type of probability that you go through a small ball. Basically, that's a huge part of all their efforts. And what they do is they actually get the asymptotics. So this is asymptotics in terms of regular distance, not conformal distance, and they show that this probability, this limit exists and equals some constant times the Green's function. The only thing I'll mention is that the constant you get here is not explicitly known, in contrast to the case where you have conformal radius, not real radius. And it's uncomputable, but it's different from the first constant. And I'm just going to say a few ideas of how the proof of these things goes. It's it's a very common theme in all of these recent papers of Greg's, and actually he kind of answered it yesterday in response after Christoph's talk. He gave an answer of how he does these things. So what you do is to get this type of estimate, you tilt by this martingale MTZ, and that makes the curve go towards Z. Right? This is how you get these two-sided radial SLE things. Then what you do is you write down, you want to analyze the conformal radius for this type of thing as the curve is going towards z. And you write down some diffusions that describe the conformal radius, and you play around and you see that typically one of them has a nice stationary distribution as t goes to infinity. And then what you do is you use fast convergence, the fact that quantities converge fastly to the stationary distribution to control the error terms of how far the conformal radius is away from things. Use sort of these things to show the probabilities of going back and forth between different points in the plane is negligible. And then the last part, I don't know. This is not a good description of it. I couldn't think of a good one though. Some integrals appear that sort of are like recursive things, and they appear to me it's like a submultiplicativity argument. That's probably not the best way to say it, but this is my take on it at least. I think Greg would probably have a different description of all these.
That's a fairly solved part of it.
The last part?
Yeah.
Yeah, I agree. It's easy, but no, I agree. Of course, the hard thing is all in this part here, the error terms, and going back and forth between different points on the plane. The curve doesn't do that. But in the paper with this most recent paper, I guess it's actually the paper with Brent, they handle that very nicely. I'll just mention that if you go back to the boundary case and try and compute the Minkowski content of the SLE curve on the real line, Greg put out a small paper, I think last year, that goes through the same idea of as what he and Mohammed did in the bulk. And all I'd say is that I think this one's a better place to start if you're interested in this type of thing. I mean, it's boundary, so it's simpler, and computations are easier, and so on. I'm just going to end here with a quick idea that I've been discussing with Frederick, and under the caveat that there's a good chance it'll never go anywhere. But so all this stuff, especially this work here about the Minkowski content, has made me think that why is this Hausdorff measure of the boundary set at least? Why is it seem out of reach still? And okay, so the idea I have in my mind at least is a soft argument to get to it. And the idea is that there is already a natural measure on the capacity times at which the curve is in the real line. That just ends up being you look at the image of the last point that has been swallowed under the SLE flow on the real line. That's just a reflecting Bessel process. It's at 0 exactly when the curve is on the real line, and a measure on that set of zeros is well known. That's just the local time. But actually, by that exact same Taylor and Wendell result, that measure is also a Hausdorff measure. The zeros are the image of a stable subordinator. So the local time measure is known to be a Hausdorff measure. And then, okay, we discussed this a few months ago with Frederick. We maybe have a way of transforming this measure on times into measure on the boundary set. And then, of course, the idea for the Hausdorff thing would be showing that does the Hausdorff measure, does the measure function transform nicely? And this would be related to a paper that, showing that this last part works, would be related to a paper that Frederick and I put out with Ilya Binder a few months ago that analyzes points on the boundary of the SLE curve where the conformal map back, its derivative behaves anomalously. So it's sort of a large deviations type result. And yeah, that's it. I'll finish there.
Thanks very much for the topic. Very nice talk. Do we have any questions?
Greg will answer any of them.
I didn't quite get your last thing.
Yeah, we shouldn't talk about that really. No, I mean, no, go ahead.
I mean, the capacity times is sort of the measure you have there is sort of on a set of points which is very special on the boundary. So how?
Actually, I have that question too.
Points where you're going to sneak through so that they have a lot of capacity. So
oh yeah, in terms of the geometry.
Then how do you transform it up in order to get something that?
Well, okay, that it's actually Hausdorff is that part. I'm very unsure about that. I mean, it's kind of a. So the way we started thinking about this is, trying to do sort of to write down the sort of the boundary bubble type construction, sort of the Balint-Verade type thing. where you conformably back, you get this Poisson point process. And for this type of thing, you need these local times on the points at which you're on the boundary, actually on the boundary. And that is just the local time boundary measure. But if you do this sort of Poisson thing, this repeated mapping back and getting this Poisson point process, the time thing has to transform into a subordinator, basically, because you get independent, sort of independent increments type thing. And so that's a very rough idea of this transformation. I mean, it's very rough. I mean, I told you, the caveat is it might not go anywhere. So.
I have a very quick question.
Yeah.
Do you think, or in fact, I'd be interested to hear from anyone, there's any prospect of finding the exact value for that C hat, the Euclidean ball probability, even in particular cases? No, I mean, it must be doable, at least in some cases, obviously.
So with the conformal radius, you get this C star because it's related to some invariant measure of the diffusion, right?
Yeah, you can write an integral for it.
Yeah.
C star.
Yeah, exactly.
C hat's not broken.
Yeah, the C hat. Yeah.
The C hat is a expectation under the
two
invariant measure,
Oh.
but not of a quantity that we know how to
Of
get the
course. I
expectation.
mean, I was sort of wondering whether there's some kind of other technology from a completely other angle to see.
Sort of expectation with respect to the typical shape when you arrive at the advisor.
Roughly speaking.
Looks pretty rough.
I have a question. I may have missed that. Do you have a Minkowski content description of the boundary natural parameterization?
Yes. So I mean, Greg does. I don't, but Greg does. So this latest paper of Greg's.
I'm sorry, what was your question?
The Minkowski content description of the boundary natural parameterization.
The boundary of
Natural parameterization. So you have
The boundary measure.
boundary measure.
The boundary.
Also describe it.
I mean, the most recent paper is the intersection of SLE with the boundary.
Yes. You have a measure. And the measure is also a Minkowski content.
It's
Yeah.
Minkowski content.
It agrees with what Scott and I did. That's his question. The answer is yes. Up to multiplicative constant.
It could not. Actually, just one comment. I mean, if you're for the zero sets of Brownian motion, if you're going to do that, you can do Minkowski content for that.
Yeah, sure.
Yeah.
Sure.
Right. If there's no further questions, I'd like to thank Tom again, and I think, okay. And I think we should also give a big round.